Hello again. This is Math 2233 coming to you from the College of DuPage, and the title of this lecture is Double Integrals with Polar Coordinates. Please be an active learner as you watch this video. Suppose we want to evaluate a double integral, the double integral over a region R of f of xy dA, where R is one of the regions that's shown here below. So either it is a solid circle centered at the origin, or it's an annulus formed by taking the difference between two circles both centered at the origin. In either case, the description of R in terms of rectangular coordinates is rather complicated, but R is easily described using polar coordinates. And recall that polar coordinates, we take advantage of this picture. This is x and y, so this point is xy, but we want to describe it in terms of r being the distance from the origin and theta being the angle taken counterclockwise from the positive x-axis, and we use this convention that r squared equals x squared plus y squared. From the Pythagorean theorem, x is equal to r cosine theta and y is equal to r sine theta. So those regions then are special cases of what we call a polar rectangle. Now this is kind of looks like a rectangle because you've got different sides. You have the inside and the outside, and you have this left side and this right side, but you see it's different because it's curved. The areas are going to be different, and so that's what we're going to have to compensate for. Okay, so in order to compute the double integral, where R is a polar rectangle, we divide AB, and that's the range that R ranges over, into subintervals. And you also divide alpha beta into subintervals of equal length. And so then we end up with circles that have R equal Ri and raise theta equal theta j, divide the polar rectangle into smaller polar rectangles. So this is a general such rectangle. You see I'm going from alpha to beta and from A to B, but now I'm dividing this into these kind of polar rectangles. So we get a picture that looks like this, and we'll focus on one of these things and then we'll add them up as a Riemann sum. So let's talk about this rectangle right here. So the center of the polar rectangle, called Rij, is going to be found, and it's just going to be the average of the R's and the average of the J's. And for that polar rectangle that looks like this, we can compute the area of Rij using the fact that the area of such a thing is a circle sector with radius r and central angle theta, and that's known from your trigonometry to be 1/2 r squared theta. Subtracting the areas of two such sectors, each of which has a central angle that's the same, delta theta, we find the area of Rij is delta ai is equal to 1/2, and then this is going to be Ri squared delta theta minus 1/2 Ri minus 1 squared times delta theta. I can factor the delta theta out, and I can use a factoring identity here to get this. A squared minus b squared is a plus b times a minus b. And then I'll use this is really the definition of Ri star. And so I get the delta AI, which is the area of this rectangle, is going to be Ri times delta r delta theta. So you see, instead of just being the length times the width, there's a compensation factor because it's a polar rectangle, not a regular rectangle. Okay, so then we'll just add them all up. So we'll change everything to polar coordinates, and we'll do the substitutions, add them up, and then we will take the limit. Now notice that this r factor is there always, so when we take the limit, what we will end up is this expression. So the double integral over region R of f of xy dA is going to be the integral from alpha to beta. That's d theta is last. That's what we almost always do. And this is going to be the integral from a to b, that is r dr. The factor of r has to still be there. And this is f of r cosine theta r sine theta. Don't forget the r, that's the Jacobian. And this talks about another way to derive that. And classically, in many books, this is how they derive this. But the important thing for you to remember computationally is that dA equals r dr d theta when we're talking about polar coordinates. So let's practice what we've learned. So let's evaluate the double integral over a region R of 3x plus 4y squared dA, where R is the region in the upper half plane bounded by the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. You know what to do. Let's see how you did. Now, whenever you graph this, you say, oh, this is one of those regions that we talked about before. So we know that theta is going to run from 0 to pi, and r is going to run from 1 to 2. And everywhere where there's an x, I put r cosine theta. Everywhere there's a y, I put r sine theta. And I use this dA really as r dr d theta. So first thing I do is I distribute the r across here, getting this, and then I'm going to integrate this dr. But remember, this is a partial integration, so theta is a constant, so cosine theta is a constant, and sine squared theta is a constant. So I perform the integral. Make sure you follow these calculations. This is the antiderivative that we get, and we evaluate it at the limits of integration using the fundamental theorem of calculus. We do that substitution and we get this as our expression in terms of theta. 7 cosine theta plus 15 sine squared theta d theta. Now I'm going to just integrate this from 0 to pi. I will do this term by term, but I have to remember that in order to integrate sine squared, I have to do that using this trig identity. So I invoke that trig identity, do the integration, and plug in the endpoints, and I get 15 pi over 2. I do expect you to be able to do calculations like this without a calculator. Here's another problem. Find the volume of the solid bounded by the plane z equals 0 and the paraboloid z equal 1 minus x squared minus y squared. You know what to do. Let's see how you did. All right. If we think about z equals 0 in the equation of the paraboloid, we get that x squared plus y squared is equal to 1. This means that the plane intersects the paraboloid in a circle, which is x squared plus y squared equals 1. That means that the plane down here, so that gives me d. So that's going to be x squared plus y squared equals 1. So the solid under the paraboloid and above the circular disk is given by this picture going up to z equaling 1. So in polar coordinates then, what I'm going to do is I have an integrand that is 1 minus x squared minus y squared, and this is dA. So it's the nature of the d and also the nature of the function that leads me to do polar coordinates. So I'm going to substitute x squared plus y squared is r squared. And this is going to be r dr d theta. And theta is going to go all the way around from 0 to 2 pi, but r is going to go from 0 to 1. So this is the integral that we set up. We distribute the r, getting this, and notice that we have this, so we perform this integral first, and so when we integrate, we get this, and we do the integral 0 to 1, and we'll get, really we'll get, I think 1/4 for that, and then we take that, and this is integrating then a constant all the way from 0 to 2 pi, so at the end we get pi over 2. Now notice that if we had used rectangular coordinates instead of polar coordinates, this would have been much messier. And in fact, not easy to do at all, because we would have had to evaluate this integral that we don't really know how to do very well. This can be done, but it is not easy. So what we've done so far is we've extended the idea to polar rectangles of iterated integrals. But we can do something more general than that, and this is similar to the type 2 rectangular regions that we did before. So now we're going to talk about a D that is going to have alpha running from, or theta rather, running from alpha to beta, but the boundaries are going to be r equal h of theta, h2 of theta out here, and h1 of theta here. And if we think about this in the same context, we'll realize that to integrate something like this over such a region D, we're going to have theta going from alpha to beta, just as before, but what's going to happen is r is going to be going from h1 of theta to h2 of theta. And this is f of r cosine theta, r sine theta, and then as always, dA is r dr d theta. And we note that if we were really talking about letting f be 1, and these be from 0 to h of theta, we get a formula that we learned in COD Calculus 2, that this area is equal to this. Now notice if we're doing it with this dA and we're changing this to r dr d theta, we are going into 3 dimensions, so the units don't match, but numerically this is true, and this formula was true more than just numerically when we did this back in Calculus 2. So here's a problem. Use a double integral to find the area enclosed by one loop of the 4-leafed rows r equal cosine 2 theta. Now this is a problem you did back in Calculus 2, but you did it a different way because we didn't use a double integral. You know what to do. Let's see how you did. All right, so here is the picture that we have, and from the picture we learn that theta goes from minus pi over 4 to pi over 4 to trace through that area. So what happens then, that area, by the theorem that we just had, is a double integral over the region D, which is this one, and that is dA. So we're going from minus pi over 4 to pi over 4, but then dA is going to be r dr d theta. And what happens is you're going to be going from r equaling 0 out to the curve, so you go from 0 out to cosine of 2 theta. So this is the integral that you set up. The rest of this is just calculation. So when you integrate dr first, you get r squared, 1/2 r squared. You substitute the top limit and the bottom limit, and we get this. This is again integrating cosine squared of something, so I have to use the double angle formula to do this, and I finish computing the integral, and I get pi over 8, just like we did in Calculus 2. Here's another problem for you, a little bit more involved. Find the volume of the solid that lies under the paraboloid z equal x squared plus y squared above the xy plane, and inside the cylinder x squared plus y squared equals 2x. Quite a bit of things to think about here. You know what to do. Let's see how you did. All right. Well, you're lying under the paraboloid. This is the paraboloid that you see right here, above the xy plane, and inside this circle. Now, this circle is moved a little bit from the origin. This center is going to be at 1, 0 and so actually it is moved just a little bit over here, and so that's the cylinder that is going up. So we're finding the volume of the solid that lies under the paraboloid but inside that cylinder. So this is what we're finding. And this is the circle that we have underneath. Okay, so in polar coordinates then, what we're going to be integrating is, this is the top minus 0, so it's going to be x squared plus y squared dA. And the domain is going to be the one that we see here. Theta is going to go from pi over 2 to, and if you look at the picture you can see that you're going from minus pi over 2 to pi over 2, and r is going to go from 0 to cosine of 2 theta. Okay, and so we're going to be going through with this calculation, and we get, we integrate first, we change this into r d, so x squared plus y squared again is r squared. dA is going to be r dr d theta, and these are the limits that we talked about. So you integrate first with respect to r, and that was r cubed, so that is r to the 4th over 4. You plug in the endpoints and you get this one. Now we're going to have to do, this is going to be cosine squared theta squared. So what we're going to do is we're doing the square of that double angle thing. We're going to expand it and do the double angle thing again. So there's a lot of algebra and trig involved from this step to this step. But then we're going to be integrating theta from 0 to pi over 2. And we do that, and eventually we get 3 pi over 2. Please make sure that you can complete all these calculations. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.